Blast furnace is often called a black box, but as senior engineers, we know it's a predictable chemical reactor if you speak its language. So today we are moving beyond guesswork and into real-time diagnostic, translating mass balances and thermodynamics into control room action. By the conclusion of this briefing, you will be able to translate mass balances into hearth control, manage the thermodynamic reserve zones for peak efficiency, and diagnose aerodynamic shifts before they trigger a slip. On the screen, you will see a blueprint schematic, a wireframe of our vessel surrounded by a cooling and gas cleaning infrastructure. So here you notice the vertical axis cross section. This is where the physics of burden doesn't meet the chemistry of the rising gases. This blueprint is not just a drawing, it's our operational roadmap for the translating complex aerodynamic into a stable hot metal production. So every decision we make start with the input material that feed this bigger vessel reactor, we can say. To control the output, we must first master the stoichiometry of the feed which is entering from the top of the furnace. So let's look at the stoichiometry of our feed. So as you can see, the diagram shows our primary inputs 70% sinter, 20% pellets and acid pellets and 10% lump. So follow the blue arrow from the left into the furnace icon. To produce 1 ton of hot metal, we are targeting 945 kilogram of iron and 250 kilogram of slag. The heavy hitter here is that gold box on the right. The B2 basicity target of 1. We can say 1.15. The so what here is critical. If your CO SiO2 ratio drifts, your slag viscosity spikes, and this leads to a poor drainage and unstable heart pressure. So we are not just dumping rock, we are managing a delicate chemical equilibrium. So if we miss this basicity target, our sulfur removal efficiency tanks and our hot metal quality also suffer badly. However, the chemical input tells half the story. The rising gas does the actual heavy lifting. Those solid input must interact with the lung of the furnace, which are measured through the gas utilization. So turn your attention to the gas exchange. As you can see, these Shanky diagram illustrate the lung of the furnace. On the left, we inject 900 standard cubic meter of in and 27% oxygen. Follow the thick blue band as it enters the tuyer. Notice the orange arrow coming down. That's the carbon from the burden stripping oxygen away. Our top gas composition on the right shows the 46%, almost 46.3 percent nitrogen, which carries the sensible heat and a gas utilization of around 46.4%. So this utilization rate or eta CO is your primary efficiency metric. If this number drop, you are literally blowing money out the top of the stack. High CO2 in the top gas means your gas is working hard to reduce iron ore. Low CO2 means you are wasting reductant. So this gas solid exchange defines the thermal profile of the entire vessel. This gas exchange creates distinct temperature zones that dictate the kinetics of the iron reduction. So we know to visualize the internal temperature gradient. The temperature gradient that is with respect to the furnace icon is a color coded from blue at the top to 150 degree. We see hematite reduction. As the burden descend to 900 degrees, we hit the austrate reduction or the thermal reserve zone. Notice the orange band at the 1200 degrees, that is the cohesive zone boundary. The most critical physical bottleneck in the furnace. So finally, at the bottom, if you'll see, the coke and gasification or coal gasification occur at 2200 degree. The operational impact is staggering. Nitrogen complete this entire vertical journey in just 5 to 8 seconds, delivering sensible heat. So if your thermal reserve zone shrink, your reduction kinetics fail. You must maintain this temperature leveraging to ensure iron is chemically ready before hitting the melting zone. If it is ready, we enter the changer of the direct reduction. So understanding these zones allow us to distinguish between efficient indirect reduction and danger of direct reduction. So this is the most important distinction for any control room operator, indirect versus direct. So on the left, in the blue safe box, CO gas reduces, postate a reaction that is exothermic or thermally neutral. Now look at the orange danger box. This is the direct reduction where solid coke react with a FeO. The chemical equation shows this is highly endothermic, draining 155 kilojoule per kilogram. The so what is a chilling furnace. If you see the bottom descent speed increase while hot metal silicon drop rapidly. For example, from 0.243 to 0.2%, you are losing the battle to direct reduction. You are consuming expensive solid coke to do a job that gas should have done higher up. To prevent this heat drain, we have to precisely control the flame temperature at the tuyer. Now coming to the flame temperature. So coming to our, if you look into the flame temperature, then we can see that how this flame temperature is also getting taken part. So this is basically look into this slide number. This is flame. So if we come to the next slide, which is on the flame, that is the so as you can see, the raft is our primary thermal control. The central gauge shows our target window, that is 1900 to 2300 max. On the left, increasing hot blast temperature or oxygen enrichment pushes the needle up, enhancing combustion efficiency. So conversely, increasing moisture, coal injection or natural gas pulls the needle down. Because of this, the endothermic reaction. As a mentor, I will tell you, watch your coal quality. High volatile matter coal can lower your flame by a maybe 200 degrees more than low VM coal due to energy required for the chemical cracking. If your flame is too low, you would not melt the slag. Too high, and you risk damaging the refractory. This thermal balance at the bottom dictates the gas pressure we feel at the top. While thermal balance is a key, the gas must actually be able to flow through the body to do its work. So coming to our aerodynamic and pressure drop part, and as you can see, the aerodynamics are the final frontier of the control. On the left, compare the coke cylinder to the center cylinder. So center is a smaller 14 millimeters versus 40, and follow those blue arrow. The gas has to twist through much tighter gaps. On over 80% of your gas flow resistance come from that ferrous burden. On the right, the bar chart breaks down the delta P. The upper furnace account for a 1.2 bar driven by the furnace, depend on sizing of different furnaces and top gas temperature. The lower furnace is 1.5 bar controlled by the state of your cohesive zone. So if your delta P spike, your permeability is falling. To double your gas velocity, you do not just double pressure, you have to increase it fourfold. This is why burden quality is non-negotiable for high productivity operations. When we push for higher coal injection, we further stress this permeability. So let's look closer at how the pulverized coal injection especially impact these gas pathways. And uh, based on these, our next slide is about the radial and circumferential symmetry. And symmetry, we know the symmetry is the hallmark of a stable operation. On the left, the radial symmetry plot shows, I will just go through that slide. Yeah. So how the gas flow and chemical utilize differ from the wall to center point. The blue lines also shows high utilization at the wall, while the orange green line shows the high temperature on the center. So these curves should be balanced. Now look at the circumferential symmetry. The Pac-Man style chart shows what happens when one tier goes off, and that's white wedge represent a massive loss of coal injection. And this is very important fundamental loss when such things are happen. And this spike local production rate, we can say it warps the cohesive zone and causes the unbalanced heat, and which has got a lot of significant effect. The action item here is a simple rotate your tube direction every 1 to 2 hours to balance top bin flow. If the furnace is not symmetrical, the math will never work and you will be constantly chasing the process rather than leading it. So when symmetry fails or the chemistry drift, we use a logic-based matrix to restore the order. So coming to our next slide, which is about a troubleshooting matrix, and it is very important one. And this troubleshooting matrix is for controlling the iron. So finally, we bring it all together, and this troubleshooting matrix, this is the ultimate key to control the iron. So top row, if you see the fast descent, dropping silicon, the root cause is spike in the direct reduction, and your action is to increase the PCI rate to restore the thermal balance. Middle row, if your upper delta P spike, your top gas is too hot and expanding, check your oxygen enrichment and look for the wall channeling. And bottom row, if the hearth is unstable, check your blast momentum. If it's below the 3000 kilogram meter per second, you likely have blocked tears injection. Mastering this math-driven diagnostic is what separates a senior operator from a uh, uh, from a think tank. So just don't just react to the symptom. Use these blueprint to fix the root cause, and I think this is fruitful.